which the numerical. Hello students, greetings of the day. So this is the third video regarding the flat slab design. In the previous two videos we covered the basic theory and the analysis part, that is direct design method of analysis of flat slab. In this video we are going to cover the total numerical of flat slab design. So definitely this video is going to consume more time, because here we are going to cover the total numerical, but to reduce that time I use the Excel sheet over here to get the optimization of time. So let's start the actual design of the flat slab. So here I have taken the statement of the numerical in terms of given data. Directly I have taken the given data. So for the design of the flat slab PT post tension flat slab, I am going to cover a panel of continuous beam, a panel of continuous slab. Continuous slab, I have taken this, I have selected the panel of the continuous slab which satisfies all the requirements of direct design method. So the details of that particular panel of continuous slab is the center to center. First detail, the center to center distance between the columns in x direction is 6 meter. Also it is going to span in y direction. The center to center distance in column in y direction is also the 6 meter. The thickness of slab, directly I have taken as the 150 mm. As per the requirement, the minimum thickness of flat slab should be 150 mm. Okay, that we discussed in the previous video. Also we have the formula to find out the thickness, that is span divided by 40, that is the empirical formula we have. But as we are going to do this design by Excel sheet, so here to get the optimum design, so I have selected the minimum thickness here. The thickness of drop, yes, the thickness of drop is depend upon the thickness of the slab. Okay, so here the total thickness of drop I have again directly taken as 225 mm. Okay, so how we get this drop thickness? So drop thickness is nothing but the addition of thickness of slab plus thickness of slab divided by 3. In this way we get that drop thickness. Here also we assume the column of size 500 mm by 500 mm, that is square column we have selected over here. Size of drop panel, again already we covered how to select the size of drop panel. So here the drop panel is nothing but the column strip width, so that is we have taken it as the 2 meter. Imposed load we considered as 2 kN per meter square for this design. Floor finish we assumed as 0.12 kN per meter square, and the length of column we assumed as 4 meter. So with these assumptions and the given data, we are going to start the flat slab design. So what is the first step to start with the flat slab design? Actually the very first step is to find out the dimensions, preliminary dimensions, but already we have assumed all these things. So we will start with the step 1 as the load calculation, because already we have all the given data. So in load calculation, first of all we are going to find out the dead load. Okay, so dead load is what? Dead load is nothing but the self weight of slab plus floor finishes. Okay, so how we find out the self weight? Self weight we are going to calculate it as the thickness of the slab into density for the unit area. And in this way, if we already we have the thicknesses, so the important point need to consider over here is for the thickness I have taken the average thickness. So see here, here we have the two thicknesses. One is the thickness of slab and another is the thickness of drop panel. So average thickness of these two I have taken for the calculation. So for this, in the column C we can see here I have put in the formula for that. So the average of thickness of slab plus thickness of drop into 24 is the density Okay, and floor finish load whatever we have, that is 0.12. So I have considered directly by putting in the formula. So the important advantage of putting the formula is there is no chance of the calculation mistakes, and it will means within a fraction of second we'll get the answer for that. So this is the advantage of this Excel sheet. Okay, so the dead load from the above data is 4.62 kilonewton per meter square. Then imposed load, yes, already given 2 kilonewton per meter square. So from this we are going to calculate the total load. So the total factored load, so I used word here total factored load. Total factored load is what? Addition of these two, addition of dead load plus imposed load multiplied by 1.5, means factor of safety we are going to apply over here, that is 1.5, and this will give us the factored load. So the total factored load for our case is 9.93 kilonewton per meter square. So this is what the step 1, that is load calculation. Now moving towards step number 2. So the step 2 is the design. Find out the design moment. Okay, so in case of flat slab, in case of PT flat slab, for the continuous slab we have considered a single panel. Okay, so here directly we cannot get the moment by using a single formula. So for this analysis of PT flat slab we are going to use the direct design method, and from this direct design method from IS 456 2000 we have this concept of design bending moment M0. So we are going to calculate this design bending moment M0 in x direction as well as in y direction, but the panel which we selected is the square shape, so the design bending moment M0 will get the same as in x direction as well as in y direction. For this analysis of flat slab we must know some terminologies, that is nothing but we have L1, Ln and L2, L1, L2 and Ln. These are the terminologies already we have discussed in the previous lecture. So let us repeat that thing. So Ln is the direction along x direction. Okay, so Ln, what we are going to take it as, Ln is the direction. It is that direction along which we are going to find out the moment, and this we are going to calculate as a center to center distance between the column minus size of the column, or there should be one check. So L1 is what? Center to center distance between the column in x direction. So this Ln should not be less than the 0.65, that is 65% of L1. So if we apply that check, L1 is what? Center to center in x direction, center to center distance between the columns in x direction, and the 65% of that is the nothing but the 3.9, means the Ln magnitude should not be less than 3.9, but as per the formula we are getting that distance as 5.5, that is center to center distance between the columns minus size of column. So out of these two we'll select the maximum. So for that I have using the maxima formula, select the maximum between 5.5 and 3.9. So we'll get the Ln distance along x direction as 5.5 meters. Then we are going to take the value of L2. L2 is what? Center to center distance between the columns in y direction, or the direction perpendicular to the x, and that center to center distance is 6 meter is given. So with the help of this given data we can calculate the value of direct with the help of this formula we can get the magnitude of design bending moment M0. So the formula for that is QU into L2 into Ln square divided by 8, where QU is what? Total load. Total ultimate load means by applying the factor load we can say L2 value is 6 meter, Ln value is 5.5. So if you put these values again, I applied the formula over here, and by putting that all values in that formula, that will gives us the value of m0 as 225.2868 kilonewton meter. So this is what the moment, but this moment is by considering the all the aspect or the total panel, means we need to distribute this moment, we need to distribute this design bending moment at various positions. How we are going to distribute that, so that total design procedure, total distribution procedure is given in the IS 456 2000 in direct design method. So we are going to follow the clauses of that. So in the step 3 we are going to distribute this m0 at various position of that particular span. Okay, so step 3 is the distribution of moment along x direction. So here for that panel distribution of moment, 4 cases, total 4 cases we are going to consider. Okay, first of all, the interior span. Suppose if we have the interior span, how we are going to distribute the moment? So for interior span we have certain coefficients. So this coefficient is for interior span, this coefficient is 0.65 m0 and 0.35 m0. So interior span positive and interior span negative. So we have positive value and negative value. What does it mean? So the interior span positive means at the center of interior span what is the magnitude of moment. So positive represent the midspan of the interior span, means we know that sagging shape is there at the midspan. So at midspan we have the positive moment of magnitude 0.35 m0. m0 value already we have calculated in the step 2. So we'll get the interior span positive moment as 0.3 times m0, and that will give us the 78.850 kilonewton meter. Okay, in the same way we can calculate the support moment for the interior span, and the magnitude of for that is the distribution factor is 0.65 times m0, which is negative because at support we have the negative moment. Hogging shape of the bending moment diagram is there. So 0.65 times m0, again I have put the formula over here. So 0.65, see here, 0. Formula bar, we can see in a formula bar 0.65 into m0, and that magnitude of moment for the interior span support is 146.436 kilonewton meter. So 2 moments we get over here from the distribution factor for the interior span. Now for exterior span we need to find out the moments. Okay, so for the exterior span we have certain coefficients given by the IS code. So for that I have prepared one table over here. Okay, so for the end span what will be the coefficients? So in the end span, so this particular end span again we divided into 3 basic part. In that the very first part is the end span exterior support coefficient. Next, end span exterior support, that already we have covered. So this is what the first end span exterior, end span exterior. Next to that end span interior support, and third one is end span middle. Okay, so we know that at support we have the negative moment. So the negative moment we are going to put the negative sign for that moments, for support moments, and for midspan moment we are going to take it as a positive moment. Okay, so what are the coefficients for that? So the in IS 456 these coefficients values are given. Okay, so I have directly taken that formulas from the IS 456 2000. So the coefficient for the end span exterior support coefficient is 0.65 divided by 1 plus 1 divided by alpha c. So this is what the coefficient for end span exterior support coefficient. Then end span interior support coefficient is 0.75 minus 0.1 divided by 1 plus 1 upon alpha c. And the third coefficient is end span middle coefficient, that is 0.63 minus 0.28 divided by 1 plus 1 upon alpha c. Means all these coefficients have one unique value, that is nothing but the alpha c. So what is that coefficient? So the alpha c is nothing but the ratio of summation of stiffnesses of all columns divided by the stiffness of slab. Means this is the stiffness ratio. Alpha c is what? The stiffness ratio. And means to get this value of alpha c, we need to calculate first of all stiffness of column and stiffness of slab. So how we get the stiffness of column? We already studied in the structural analysis too how to find out the stiffnesses for the various members. So the column, for the column of square shape or the rectangular shape, the stiffness coefficient factor, the stiffness coefficient is given as 4 EI by L. Means for this stiffness we must know the value of E, we know the value of I and value of L. So we are not so E, as we are going to do this calculation for the RCC, we are not going to put the value of E over here because it is common, and as this is the ratio, so it is going to cancel in the further calculation. So we are going to keep that E as it is. Now I is the moment of inertia. Moment of inertia for the column is of having square shape 500 mm by 500 mm. So for that we need to calculate the value of I. So as it is the rectangle, we can use the formula for I as 112 b d cube. So again I have put the formula over here, 112 b into d cube. So when we put all that values of b and d in this formula, we get this moment of inertia for the column as 0.00512 meter raised to 4. So here I have calculated that values of moment of inertia in terms of meter raised to 4, not in terms of mm raised to 4. Okay, so by using this we get the moment of inertia I. E we are going to keep as it is, and L is the length of column. So in the given data we assume that the length of column is 4 meter. So with the help of all these data we'll get the value of Kc as, so when we put all that data over here, so E we are going to keep as it is. So this value of Kc is in terms of E. Okay, so 4 into I divided by 4, so that calculations gives us the value 0.00512. Okay, so already means the direct formulas I have used, so no need to do the calculations manually. So it will save our time. In the same way, we need to calculate the value of coefficient. We need to calculate the value for stiffness for the slab. So for slab, how we are going to calculate the stiffness? Again, for that we require the moment of inertia and length. So for this slab, for moment of inertia calculations, we are going to assume the B value as 1 meter. 1 meter width we are going to consider, and the thickness, the depth we are going to take as the thickness of that slab. So by using the above data, already we have the thickness of slab, already we have the we assume that 1 meter width. So by using 1 meter width and the thickness, by using formula 112 bd cube, we can calculate the value of that moment of inertia for the slab, and that value is 0. Here I have put the formula over here, 112 bd cube, and the value is 0.0057. So this is the moment of inertia for slab. And the length of slab, again we are going to consider as length of spans here. Again I put the formula. So B4 is nothing but the center to center distance between the column X, that is 6 meter, I have considered as the length of slab, because we are calculating the moment in the direction of X. So this is gives us the value of stiffness, and once we get these two stiffnesses, the ratio of these two gives us the value of alpha C. So see here, the ratio of these two, again the formula is put it. So that ratio gives us the value of alpha C as 1.372. So this alpha C we are going to put in this formula, so that we'll get the coefficients values for the three different cases. So when we put this alpha C value, we'll get the end span exterior coefficient as 0.3759. We'll get the end span interior coefficient value as this coefficient value as 0.7078. and if we put that value of alpha C in this expression, in this formula for the coefficient, we get the coefficient value as 0.468. okay, and if we multiply this coefficient to the value of m0, we'll get the moment in that particular position, means at that particular position we'll get the moment. So see here, if we want the moment at the end span exterior support coefficient, we need to multiply this coefficient to m0. So this coefficient into m0 gives us the value of moment. So that value is 84.694 kilonewton meter. So this is the moment, negative moment at end span exterior support. At the same in the same manner, we get the end span support end span interior support moment, that is negative in nature. So if you multiply this 707 by m0, we'll get this moment. Okay, so already I put it the formula. So that will gives us the moment magnitude as 159.466, which is negative in nature. Support moment is negative, and the last moment we get as the end span middle moment, that is this coefficient is 0.468 multiplied by m0, that gives us the magnitude of moment as 105.447 kilonewton meter. And in this way, with the help of IS code direct design method, we can find out the magnitude of moments at various span for the exterior and interior panel. Okay, so this is what the summary of that distribution of moment along x direction. So the interior span negative, interior span positive, end span exterior support, end span interior support, and end span middle moment. So these are the moments we are getting with the help of analysis method, that is direct design method of analysis, and these moments we are going to use for the further calculation. Now the further calculations, the step 4 we have. Okay, 1 2 3 start. Step number 1 2 3 start. Now the step number 4. So after the step number 3, that is the analysis of PT flat slab, in step number 4 we are going to start our actual design of prestressing. So for prestressing design, the very first important factor is the calculation of prestressing force. So we get this magnitude of prestressing force with the help of moment which we calculated in the step 3. So see here, so this is what the moment calculated. We have the different position moments we have. So we calculate this prestressing force for the maximum bending moment. So first of all we are going to select the maximum bending moment from this. So where we get that maximum bending? Here. So here we have that maximum bending moment. So that is for the end span interior support. So irrespective of its position, we are going to focus on the magnitude of that moment. So for this maximum moment, we are going to calculate the value of prestressing force. So how we get the prestressing force for the moment? We know the basic formula. Moment is equal to force into perpendicular distance, that is lever arm into force, that will give is equal to moment. So that will give us the prestressing force value. So already so for that reason we require two things. One is the moment we have, and to get this value of prestressing force we need to find out the perpendicular distance, that is the lever arm. So to get that lever arm distance, first of all we are going to consider the cover for the particular slab, because we know that prestressing force value, so when we take the maximum lever arm, means when we use the optimum value of the lever arm, we will get the minimum value of prestressing force. Okay, so see here, so we'll get this prestressing force by using the theory of moment. Okay, so to get that lever arm, first of all we are going to assume the cover for that particular slab of as 30 mm cover I have considered. Okay, then the eccentricity in the mm at support. So how we get the eccentricity? So actually see here, the position of prestressing steel is very important in case of prestressing. When we change the position of prestressing force, it will affect positively and negatively as well. So that's why when we put that prestressing steel at extreme position, means when we have that maximum eccentricity, we'll get the maximum then we get the good results for the prestressing force, even without increasing the number of tendons. So that's why we have taken the maximum eccentricity over here. So how we get that eccentricity? How we get that eccentricity? Total thickness divided by 2 minus this cover will give us the eccentricity, and then the current distance. How we get the current distance? Current distance for rectangular panel or the rectangular shape is h by 6. Already we also derived this during the theory lectures. So for rectangle, that current distance is h by 6. Okay, so h by 6, h value already we have. H is nothing but the thickness, total thickness we are going to consider as the h, and divided by 6. So we'll get this current distance also. Now we have the eccentricity, we have the current distance, and we have the maximum moment. So how we get that prestressing force? So final prestressing force is equal to P minus, so this final prestressing force, how we get? So final prestressing force is nothing but the moment divided by that curve. Okay, moment divided by curve or that lever arm distance. So that lever arm distance is nothing but the addition of current distance plus eccentricity. Okay, so formula already we have in the PowerPoint presentation also. I have given that formula to find out the prestressing force. So many times we use that prestressing force formula, so that's why intentionally I haven't put that formula over here. So that will give us the prestressing force. So that magnitude is 1328.88 in kilonewtons. But this is what the final prestressing force. So to get this final prestressing force, we need to provide additional prestressing force, because finally we are going to get this value. But means this value we are going to get after some losses. Means initially if we apply this much amount, then it is going to reduce. further, so that's why we, for initial value of the prestressing force, we need to increase it by 20%. Okay, so that's why we get this P initial as P final divided by 0.8. Okay, P final divided by 0.8. So this is nothing but the prestressing value for, this is the initial prestressing value, prestressing force value, and this is the final prestressing force value. Now we have the value of prestressing force. Now what we are going to do? So once we get the value of prestressing force value, now we are going to calculate how many number of tendons we required for the prestressing. Okay, so we are going to provide these tendons at various positions. So what are that positions? One is the interior span support, interior span mid, interior span mid, interior span end span exterior support. Means basically we are going to divide it into two zones, that is what the interior zone, and this we are going to call as the exterior zone. So in the interior zone we are going to provide, because already we have calculated the moment, so wherever we calculate the moment, there we are going to provide that tendons. So the position of that, how we are going to decide the position? So position of that tendon is nothing but its eccentricity. So the formula of eccentricity is nothing but moment divided by P. So that is prestressing force, which we calculated over here. So the prestressing force minus K. K is what? Kern zone. Again, I haven't put any formula over here because formula, I haven't put that prestressing diagram over here, because many times I used to show that stress diagram for the design of beams, for the design of one-way, two-way slab. I have shown that stress distribution diagram, so that we'll get the idea how we get that formula for E. Okay, but as it is repeated many times, so I haven't put that prestressing distribution diagram over here. So you just remember this formula E is equal to moment divided by P minus K. K is nothing but the curve zone. Okay, so moment value already we have for the interior span. Prestressing force value we have, see here, for prestressing force value we have taken as the final prestress value. See here, B56 means we have used the final prestress value, because this formula is for the final, based on the final stress diagram we use this formula. So though we get the eccentricity as with the help of this formula, eccentricity at interior span support is 72.7, eccentricity for the interior span mid is 21.8 mm, and for the exterior panel we have the three eccentricities. One eccentricity at the end span of the exterior support is 26.2, end span interior support eccentricity is 82. See here, everywhere I have the same formula I used, and for this formula I have directly given the values, because already we have calculated the moment, we have the prestressing force, and also we have the curve. Okay, so by using all that, directly we will get these eccentricities at various positions. Now we have the eccentricities for the 5 different positions of the prestressing steel. So this is what the step 5, that is calculation of permissible tendon zone, or finding out, we can say the finding out the eccentricities. Now the step number 6. Step number 6, yes, now we have decided that where to provide the steel, up to what value of prestressing force we are going to prestress, that also we have. Now it's time to find the number of cables. Okay, so for that, for our design we are going to adopt 4-12.7 diameter high tensile strand with an initial stress of 1800 MPa. So we are going to use this type of strand, 4/12.7 mm HT strands we are going to use. Okay, So each strand capacity is 1800 MPa. Now area of each strand is also we have taken. Actually we can get this all this data from IS 6006. Okay, so the area of each strand for our selected strand, the area is 98.7 mm square. Then the design stress in each strand is 1368 MPa. Now how we get that design stress? Actually means the capacity is initially we have selected the capacity as 1800 MPa, but the design stress we are going to consider as the point 76, means we have considered the 76% of its total capacity, that we are going to consider as the design stress, which is given in the clause 19.5.2. okay. Now once we get this, now we can calculate the total area of the cable consisting of the 4 strands. Now see here, we are going to use the cable. Okay, our cable is going to consist 4 strands. Okay, means whatever details I have provided over here, add of 4-12.7 means in this cable 4 strands are there. Area of each strand, diameter of each strand is 12.7. okay, and here the details of single strand is given. So the total area of the cable, how we get the total area of cable, means in that cable 4 strands are there. So 4 into area of single cable. So directly I put the formula over here, that see here 4 into row number B66. So that will give us, means in very short way we can say that we are calculating the number of cables, and here we use the cable which is having 4 strands. Okay, so the total area of cable is 394.8. now force in each strand, how we get the force in each strand? We know the relation between the force, stress and area. Stress is equal to force divided by area. So by using this basic expression in the reverse way, we can get this force. So force is equal to stress divided by stress into area. So see here, this is what stress into area. Stress into area gives us the force in each strand. Okay, so for the stress in single strand into area of single strand, means B66 and B67. So B66 position is what, this one is the B60 area of each strand multiplied by design stress in that strand gives us the force in each strand. And basically we want the force developed in the cable. So the force in each cable, how we get? We are going to multiply this force by 4, because in a single cable 4 strands are there. If the single strand carries 135, then force in each cable gives us the 4 into 135.02, that is 540. I have put it the formula. See here, we can see here 4 times this B69. So in this way we get the force developed in the cable. Now the total force required. For a width in x direction. Now see here, we are going to provide these cables in the x direction, because whatever moment is there in the x direction, to resist that moment in x direction, we need to provide the cables in x direction. So this is what the force in a single cable, but we want the force in entire direction. So for that, here what I did is I have multiplied this force in each cable by the B4. What is that B4? We can see here B4 is nothing but the total span in the x direction, that is center to center distance between the column in x direction, that is 6 meter. Okay, so from this we get the total force. Now this is what the total force we have, but we don't have any cable to take this type of load, this total load. Our cable is going to take this much, so this is what the maximum capacity of our cable. So 540.0864 is the capacity of the single cable, and we have the total force of 9966.6477 kilonewton. So to take this total load we require more number of cables. So how we get that number of cables? So this total force required divided by force in the single cable, that will give us the number of cables. So again I have put the formula over here. So that will give the number of cables as 18.45, means approximately 19 cables were required in x direction to overcome the moment in x direction. Okay, now so these total 19 cables, how we are going to provide? Because in the analysis part, also in the basic of the design of PT flat slab, we are going to divide the slab into various strips, that is the column strip and middle strip we have. So we are going to divide this 19 number of cables in the two spans, or here approximately 12 plus 6 means 18 I have considered over here. So the out of these total 18 cables, we are going to provide 65% cables in the column strip and 35% cables in the middle strip. Why this is so? Because we know that whatever moment we are getting, that maximum moment we are getting at support, means in the column zone. So that's why we are going to provide this 12 number of cables, that is 65% cables in the column strip and 35% cables in the middle strip, that is 12 number and 6 number. So how we get the spacing? Yes, we know that 12 number of we are going to provide, 12 number we are going to provide in the column strip. So what is the spacing between the two adjacent cables? So that spacing we are going to get as the total column strip width divided by 12, right? So that will gives us the 250 mm and 460 mm, means we need to provide the cable at a distance of 250 mm in the column strip, and we need to lay the cables at a distance of 464 mm in the middle strip in x direction. Actually we have the square shape, so we are going to provide this type of cables spanning in column strip and middle strip for x and y also. Now so this is what the here we done our